Hi, welcome to the second video in the series about the golden ratio, where we sort of talk about a mathematical explanation as to why the golden ratio seems to be found in many places in nature. So, if you recall from last time, we had the Fibonacci sequence. So it was 1, 1, 2, 3, 5, and so on and so forth. And we had another labeling for some of these numbers, and that was F0, which corresponded to 1, F1, which corresponded to the second one, F2, F3, F4, and so on. And this just lets us label which position in the sequence of Fibonacci numbers any given number has. So the other thing that this lets us do is write down as an equation the defining feature of the Fibonacci sequence. Recall that the way that we obtained new numbers in the Fibonacci sequence was by adding together the previous two. So we started with 1 and 1, we add those together to get 2, then we have 1 and 2, we add those together to get 3, we have 2 and 3, we add those together to get 5, and so on and so forth. So one way we can express this as an equation to describe how to obtain new Fibonacci numbers is if we write the expression Fn is equal to Fn minus 1 plus Fn minus 2. So what this is saying is that in this case n is just some arbitrary integer or natural number. This is telling us how to compute the nth Fibonacci number from the two previous ones. So for example, if I wanted to compute F4, I would have to first compute F3 and add F2, right? And so this here is just saying, right, we know that F4 is 5, looking up here, and F3 is 3, F2 happens to be 2. So that's just expressing this identity here. But now, the nice thing about this is mathematicians really like to work with equations. That's not the only thing that mathematicians work with, but it is one fundamental tool that we have to express ideas. And so this equation right here allows us to capture the idea of the golden ratio. So the other thing I want to talk about before we get to the good stuff is this idea. Recall last time we also had that successions, different numbers, we had 1 over 1, right? If we divided successive Fibonacci numbers, these slowly got closer and closer to the golden ratio, whose actual value, well, it's an irrational number, so it's impossible for me to write down all the digits, but it starts something like this. And notice this estimate here, it undershoots it a little bit. This one overshoots it a little bit. This one undershoots a little bit. If you keep going, if you look at some of the calculations I did in the last video, they alternatingly over and undershoot this number, this golden ratio. So we want to write some other type of mathematical expression that captures this idea of the fact that the further we go along, the closer and closer we get to the golden ratio. Of course, again, because the golden ratio is an irrational number, none of the choices in our sequence are ever going to exactly equal the golden ratio. Because these are all rational numbers, their decimal expansions either have a repetition at some point or they terminate, which is the same as having a repetition of zeros. So even if we took, F 1 million and 1 and divided it by f 1 million, this would be much closer to the golden ratio than certainly the calculator in your pocket could tell the difference between. And I think for any practical intents and purposes, if you were trying to build something that had the dimensions of the golden ratio, you couldn't possibly need anything that was this accurate. But the point is that this will still fail to be exactly the golden ratio. However, if we keep increasing the numbers down here, the Fn, this ratio for higher and higher pairs of Fibonacci numbers will always become a better and better approximation, so much so that we can actually make the approximation as close as we like. So what I mean by that is you can pick any tiny number imaginable. So let's say you pick the number 1 divided by 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. 0 0 0 0 0 0 0 0 0 0 0 0 0. Okay? That's going to be a pretty small number, right? It's 1 divided by a very big number. And if you give me this number and you said, okay, I want you to find some pair of Fibonacci numbers, some Fn and some Fn minus 1, so that when I take the ratio, I want the difference between this and the golden ratio to be less than this number. And it turns out one of the nice properties, the relationship between the Fibonacci sequence and the golden ratio, is that no matter what impossibly small number you give me, I can always find some big enough n, some Fibonacci number far enough down the line that dividing it by the number that came before it will be off by less than this distance from the actual golden ratio. So in mathematics, mathematicians have developed a really sort of nice concept or a nice notation, I guess, if you will, to express this idea, and that's the idea of a limit. So what we say is that the limit, or just lim, as n approaches infinity, so we write n with a little arrow here, of Fn over Fn minus 1 is equal to the golden ratio. So again, what all this means, so this is just some fancy notations, right? So this n with an arrow pointing towards the infinity just means that, the n, we sort of think about the n is getting bigger and bigger. We can make it as close to infinity as we like. And the limit, so this whole gadget here, this whole piece of notation, this is all just a shorthand to express the idea I was just saying, which is that no matter what small number you give me, it could be anything, as long as it's a small number bigger than 0, any impossibly small number you could give me, I'll always be able to find a big enough n so that the difference between this ratio and the golden ratio is less than whatever small number you give me. So that's what this notation here is expressing. So, okay, I've told you that this is the golden ratio, and it looks like it's the golden ratio, but we can basically derive this result ourselves. And so we're going to do that right now. I'll admit there's a little bit of cheating going on because technically, if you haven't taken calculus or any real analysis, you can't necessarily be sure that we can do things like division and addition and just pop them inside and out of a limit. So maybe I'll make some videos on that at a later time, but for now, if you're not familiar with that, you might just have to take it on trust that we're allowed to do those sorts of manipulations. So I'm going to start with the defining equation of our sequence. So Fn is equal to Fn minus 1 plus Fn minus 2. And now I'm going to divide both sides of the equation by Fn minus 1. So we get fn divided by fn minus 1. That's going to be equal to fn minus 1 divided by fn minus 1 plus fn minus 2 divided by fn minus 1. Okay, so now what we're going to do, so just to clean things up a little bit, we get fn over fn minus 1, and fn minus 1 divided by fn minus 1, well, these are just the same thing, so that's just going to be 1, and this becomes fn minus 2 divided by fn minus 2. So if I take this expression, and now what I'm going to do is I'm going to calculate the limit over here. So this is exactly the limit that we're looking for. But now we've got it, we're relating it through this equation to a different object over here. So let me just quickly erase what I've got on. Okay, so what we're doing is this equation down here, I'm taking the limit of both sides. So I'm going to get the limit as n approaches infinity of fn over fn minus 1. And this side will be the limit as n approaches infinity of 1 plus fn minus 2 divided by fn minus 1. Okay, so what do we do with this? Well, so these are our Fibonacci numbers here, right? These are the ratios that we're interested in. And we're trying to show that this limit actually is the golden ratio. So let's pretend for a minute we don't know what this limit is. It definitely seems to be converging on some number, but it's possible from what we looked at before with our ratios, maybe it's off from the golden ratio by a small amount. So I'm going to call this expression here the limit of fn over n minus 1, I'm going to call this delta. I'm going to use the Greek letter delta. So this side right here is, by definition, this thing I just called delta. Now the limit of 1 plus fn minus 2 over fn minus 1, I can pull this 1 out in front here, and that can just come outside the limit. So again, maybe that seems like a reasonable thing to you, maybe it doesn't, but that is something that would be proved in, say, a first-year analysis course. So maybe I'll make a video about formal limits later on. So now what I get is the limit of fn minus 2 over fn minus 1. And notice, though, the idea of a limit doesn't really matter where you start in the sequence, right? Because it's something about what eventually happens, right? So if I started the Fibonacci sequence at 5 instead and just went, say 5 and 8, and then went 5 plus 8 is 13, and 8 plus 13 is 21, and so on, and say I decided to call F5 F0, and 8 was F1, and 13 was F2, well, this wouldn't really change the fact that my approximations, like 8 over 5, 13 over 8, 21 over 13, these are the same approximations that occurred in the other sequence of Fibonacci numbers when we included the lower numbers over here. And so it really doesn't change what the limit is going to be, because it says what these numbers, this infinite sequence of numbers, eventually gets really close to this. So chopping off the first few doesn't really make a difference. In other words, I can change the indices here. I could add 2 to both of these indices. So I can shift the whole sequence over. I'm actually going to shift the whole sequence over by 1. So this becomes fn minus 2 plus 1, which becomes fn minus 1. This becomes fn minus 1 plus 1, so that's just fn. And now look, if we look at this limit over here, this is just we're flipping the fraction around from this limit. And so if you remember some basic rules of fractions, we have that a over b is just, say, 1 over b over a. So what that really means, since our original limit here we were calling delta, that means that this limit over here is really just 1 over delta. Okay, so now we have an algebraic expression with delta. And now, in order to use a little trick from high school, I'm going to multiply both sides by delta. So over here I'll get delta squared. This will be 1 times delta, which is delta, plus delta times 1 over delta. Well, that's just delta divided by delta, so that's 1. Now if I move this over, the delta and the 1 over to the other side of the equation, notice that this really just looks like a quadratic equation, right? This sort of looks like the equation x squared minus x minus 1 equal to 0. Well, in fact, it is a quadratic. So what that means is I can use the quadratic formula, which says for some polynomial, if the coefficient here we called a, and the coefficient here we called b, and the coefficient here was c, the quadratic formula tells us that x, the solutions which make this equation valid is negative b plus or minus the square root of b squared minus 4ac divided by 2a. So if we look at this equation for delta, we get that delta is equal to, so b here is negative 1, so this is the negative of negative 1, which is 1. We get plus or minus b squared, the square root of b squared, which is 1, minus 4 times a, which is 1, times c, which is negative 1. And finally, we divide by 2a, and a is equal to 1. So we get 1 plus or minus the square root. So negative of negative 4 is positive 4, so this becomes 5 over 2 times 1. And so we're almost at our answer. The problem is this gives us two answers, right? 1 plus the square root of 5, 1 minus the square root of 5. Well, turns out the square root of 5 is larger than 1, so 1 minus the square root of 5 would be a negative number. And clearly, that would be nonsense, right? Because we're taking a sequence of positive numbers, right? Dividing these sequences of positive numbers. So there's no way, as these positive numbers get larger, there's no way we could ever have a negative in here. So the solution must be when we have this plus sign. In other words, delta, which was our limit, is 1 plus the square root of 5 divided by 2, and this is the golden ratio. Okay, so what was the point of this whole exercise? I already told you that the limit of this was the golden ratio. Well, this is the punchline of the whole video series, because nowhere in this derivation did I actually use the fact what the starting numbers f0 and f1 were. Remember how I said I could, say, shift that sequence? So, for instance, if we look back at the steps, all I did was start with this equation. Fn is equal to Fn minus 1 plus Fn minus 2. I started with this equation, and from this, I was able to manipulate just using some algebra and the quadratic formula and discover that the limit of the ratios was the golden ratio. But the thing is, I could have started with almost any number. Well, I could have started with any number. I could have taken f0 to be pi, and I could have taken f1 to be 1000. And even if you start with these two numbers, the proof that we just showed showed that the golden ratio would still end up being the limit of these fractions. So those fractions would still approximate the golden ratio as well as you wanted, as long as you made the number in the sequence large enough. So what does this tell us? This tells us that the golden ratio doesn't have a special relationship with the Fibonacci numbers, but it does have a special relationship with this equation here. So let's think about that. So that's kind of interesting. Of course, the Fibonacci numbers fit into this recursive definition, but there are many other sequences that we can define depending on what two starting values we use. Of course, the one thing is these couldn't both be 0, because then we would always just get 0, and when I was dividing by fn, that wouldn't be allowed because we're dividing by 0. So that's the one case it wouldn't work out. But it's important to note that this would still play out in for any other choices of starting numbers. So the thing is, the golden ratio has a special relationship to this equation here. And what is this equation telling us? Well, it's telling us to build something, in this case a number, based off the previous two existing things in the sequence. And that itself seems like it would come up in nature quite often. It seems like a pretty simple process, right? You build something new out of the two things that you already have present. So I think this little derivation here, at least to my mind, again, there's many other reasonable explanations. Humans like to find patterns in find patterns in nature. If you look hard enough, you could make any number seem to appear everywhere. But this is interesting because it does offer a mathematical perspective of why we might find the golden ratio everywhere. It's just off a simple principle that, well, to build something new, you got to start with the two things that were already there. Okay, thanks a lot. If you have any other videos that you want me to make, any other mathematical questions, please let me know, and I will take requests. Advanced math, introductory math, I'll do it all.